Welcome to The Explainer. Today, we are diving into a huge question by looking at two completely different ways to measure human history. We're going to break down the starting points, the big assumptions behind each timeline based on the research we've pulled together. All right, let's just jump right in with a question that sounds super simple, right? How old is humanity? I mean, it's one of the most basic questions we can ask about ourselves. But what you're about to see is that the answer you get completely depends on where your starting line is.
So you've got one framework that says, hey, humanity is about 300,000 years old. And then you have another one that says, nope, it's more like 6,000 years. I mean, that is a massive difference. We're not talking about a small rounding error here. The gap is just huge. And the reason for this gap, it isn't really about science versus faith. It's all about the different, unprovable assumptions that each model is built on from the very beginning.
Okay, so let's start pulling these two timelines apart. We'll begin with the secular genetic model. And a great way to think about this one is like a chain of logic, where every single link is a critical and unprovable assumption. The very first link, the one the whole thing hangs on, is the date of the human-chimp split. You see, the entire molecular clock they use to date our most recent common Y-chromosome ancestor, well, it's all calibrated or set using this idea that we split off from chimps something like 6 to 7 million years ago. And where does that number even come from? Well, it comes from interpreting bits and pieces of fossil evidence. So that 6 million year date is the anchor for absolutely everything that follows. It's the model's biggest weak spot. If that interpretation of the fossil record is off, even by a little, the entire timeline shifts. It's the very first link in the chain, and if it breaks, the whole thing falls apart. Okay, link number 2 in our chain is the assumption of a constant mutation rate. The model uses what's called a phylogenetic rate, which it gets from that human-chimp comparison. Basically, it has to assume that genetic mutations just tick along at this slow, steady pace over millions and millions of years. Kind of like a perfectly reliable clock. But here's where it gets really interesting. This assumed slow rate, it directly contradicts the much faster mutation rate that we can actually watch happen in the real world right now by studying fathers and their sons. This is called the pedigree rate. And the huge difference between the two creates a major problem for that deep time math. You know, depending on which rate you use, the date for our common ancestor can be all over the place. And finally, to turn a bunch of mutations into an actual date in years, you need one more assumption, the average length of a generation. Most of these models just plug in a number, usually somewhere between 25 and 30 years. But that's just an estimate, right? Some anthropological data actually suggests that way back in the ancient past, generation times could have been a lot shorter, maybe closer to 15 or 20 years. Think about it. If people had kids when they were younger, that would dramatically shrink the entire timeline. So you can see how that 300,000-year number is really just the final product of a specific chain of very debatable assumptions. Okay, so now let's switch gears and look at our second framework. Instead of starting with these deep time assumptions, this model starts with specific numbers that were written down in historical texts, and then it tests whether those numbers are even mathematically possible. Our starting point here is in the book of Genesis. It gives a really specific number. It says the house of Jacob, that's the founding group of the Israelites who went down into Egypt, was made up of exactly 70 people. So how long were they actually in Egypt? Well, some passages mention 430 years, but historical analysis, including from the historian Josephus back in the 1st century, suggests that number includes the time the patriarchs spent in Canaan. The actual time the population was growing in Egypt was a lot shorter, more like 215 years. And then, at the end of that 215-year period, we get another incredibly precise number. A census was taken at the Exodus, and it's recorded in the Book of Numbers. It counted 603,550 men old enough to fight. Now, that doesn't even include women or children or the entire tribe of Levi, so we're really looking at a total population of well over 2 million people. So, is that even possible? I mean, seriously, can you get from just 70 people to over 2 million in only 215 years? That sounds like an absolutely insane population explosion. Let's actually run the numbers and see if it holds up. Okay, so here's how the math breaks down. You start with 70 people, you have 215 years for them to grow. If we assume a generation is about 25 years, that gives us about 8.6 generations. To get to over 600,000 men, the math shows you need an average of 2.73 surviving sons per man per generation. So that means each family needed to have about 5 or 6 kids who survived to adulthood. And while that's a pretty fast growth rate, it's not impossible. It's actually been documented in other real historical populations when conditions were right. All right, let's zoom out and scale this up. We can use the very same kind of math, but this time apply it to the entire global population, starting from the biblical account of the flood survivors. So in this model, we start with a population of just 8 people. That's Noah, his wife, his 3 sons, and their wives, about 4,500 years ago. The big question is, what kind of growth rate would it take to get from just those 8 people to the more than 8 billion people we have on Earth today?
Well, the answer is surprisingly small. It only takes an average annual growth rate of 0.48%. That's less than half of 1% per year. To give you some perspective, the global population growth rate actually peaked back in the 1960s at over 2% per year. So a steady rate of just under 0.5% is really, really conservative. And this really shows you the power of an average rate. You might be thinking, well, what about all the wars and plagues? And you're right. Things like the plague of Justinian or the Black Death were absolutely devastating to the population. But that very conservative 0.48% average easily absorbs these huge population shocks. It balances out the bad times with periods of much faster growth, like what we saw after the Industrial Revolution kicked off.
So we've taken apart that chain of assumptions behind the big genetic model, and we've pressure tested the numbers from the historical model. So what's the big takeaway here?
It really all boils down to this. The secular model asks you to put your faith in the interpretation of ancient fossils and the idea of a constant molecular clock, even when there's real-world evidence that contradicts it. The biblical model, on the other hand, asks you to put your faith in a documented historical story, one that actually turns out to be mathematically plausible when you put it to the test. Which leaves us with one last question for you to think about. Which set of starting assumptions provides a more coherent framework for understanding our past? Is it the one built by setting clocks to fossils from a presumed deep past? Or is it the one built by testing the numbers in a preserved historical record? The answer to that fundamental question, how old is humanity, really does depend on which foundation you choose to build on.